Welcome back. As promised, here's a short video on R squared. So R squared is a famous, some would say notorious, measure of linear regressions and how well they fit the data and explain a relationship between variables. So we've already talked about correlation. We have two quantitative variables, x and y. We can take a measure of the relationship between those variables called the correlation. There was an equation for it. I told you you didn't have to know it. That remains true. You don't have to know, but you do have to know some properties of correlation. If you recall, correlation is a number that's between -1 and 1. So things that are close to 0 are indicating there's not much of a relationship between these variables. As you go closer to 1, then we see a strong positive relationship. As you get closer to -1, you see a strong negative relationship. But so the correlation was a number that we could use, and so far we did it to kind of look at a scatter plot. We described what direction and strength the relationship was there, and we said, okay, the correlation can help us kind of confirm or deny what we saw, our objective impressions, subjective impressions, when we looked at that scatter plot. Here was an objective measure that could kind of confirm or deny that for us. Now, the correlation between two numbers is often written as R. If we square that number, so again, it's going to be a number between -1 and 1. If we square it, we end up with a positive number, because all real numbers are positive when they're squared. And we're going to end up with something that's between 0 and 1. Now, that's true because you take a number that's smaller than 1, you square it, it's going to get smaller because you're multiplying it by itself and it's smaller than 1, right? So at the extremes, you have, say, -1, you square that, it becomes 1, positive 1. If you have positive 1 as a correlation, you square it, it becomes 1. If you have a correlation of 0 and you square it, it remains 0. Everything is going to be between 0 and 1 when we are looking at R squared. Now, this is a measure that you see used a lot because it actually has a really nice interpretation. So if we fit a line to data, that line is trying to capture what's going on with the relationship between the variables x and y. The R squared is a measure that tells us what percent of the variation in y, that variable we're trying to understand more about, what percentage of that variation is explained with this linear model based on changes in x? Or a way to think about it is, how much of the changes in y can I understand based on looking at changes in x and the simple linear relationship between these two variables? So if I have a correlation of 0.5, if I square that, it's going to be 0.25 because I'm multiplying 0.5 by itself, right? What that means is that 25% of the variation in the y variable is explained with changes in the x variable. And this linear relationship that we've, put that simple linear line through using the ordinary least squares technique that we talked about before. So we see R squared used a lot because it has that nice clean interpretation of, this regression is picking up 2% of the variation in y, or 92%, right? And we really do see numbers all over the place when it comes to R squared. It tends to be, if you're looking at something like lab data in the natural sciences, you often see R squared that are very high. And if you think about it, that makes sense. We're talking about stuff going on in a lab where we're controlling all the conditions except whatever we're adjusting that's of scientific interest. And so in lab conditions, the changes that we're interested in, the changes in x, can explain a big amount of the changes in y because that's really the only thing that's changing other than very small stuff that's beyond our control, randomness that happens. So the linear model will explain 95% with an R² of 0.95. If we're looking at human behavior is a lot messier than most lab data. So if we're looking at how much people decide to save for retirement or something like that, we might look at how a change in an employer matching program for their retirement thing, how that's affecting how much people choose to save as they're setting aside money for retirement. The change in the employer matching program might help us explain how much people set aside, but it's probably not going to be a huge percentage because people set aside different amounts for retirement for all sorts of other reasons beyond how much their employers match things. So we might have a regression of that sort of behavior and explain 6% with an R² of 0.06. So that would mean 6% of the variation in employee retirement savings is explained with employer match programs. That means 94% of personal retirement decision is not explained by employer match programs. That's not necessarily bad. It doesn't mean it's a bad regression or a bad relationship to understand with these variables. The R² tells us how much of the variation this linear relationship explains, but it doesn't tell us that it's a good regression or not, because that really depends on the context. What question are we asking? What are we trying to look at? In some cases, again, if you're in a science experiment lab setting, an R² of 0.7, so 70%, might be unacceptably low. But if you're looking at some decision about how firms are deciding how many employees to keep and how many to let go during these crazy times with virus going around and all kinds of different restrictions on people's movements and such, I mean, that's a decision that's going to be based on a whole lot of different things. So looking at any one factor for an X value is probably not going to explain much at all. You might have an R² that's 0.1 and you're explaining 10% of the variation. That might be really good. Maybe you'll explain 1%, 0.01. That might still be worthwhile depending on what you're looking at, the context. So there's no magic threshold for when an R² is big enough. Often when people are looking at the same outcome, the same sort of context, and you have two different things to two competing linear models to try to explain what's going on, that's the sort of time when people will often look at the R² and say, well, this model picks up more of the variation. This one picks up 60% of what's going on. This one only picks up 40%. I'm going to go with the one that picks up 60% of the variation in Y. So if you're looking at a similar context and you have competing models, that's a time when R² can be really useful to kind of help decide which model does a better job picking up what's going on. We'll be talking about predictions in this class, and so R² is helpful for kind of keeping context in mind when it comes to predictions. If you have a prediction model where that model is explaining 90% of what's going on, then you can feel pretty good about the predictions coming out of that model. If you have a prediction coming out of a linear model that explains 1% of what's going on, that's not one I'm as likely to put money behind those predictions, if that makes sense. If the linear model only explains 1% of the variation in Y, that means 99% of the variation in Y is not explained with the model. That means that model's predictions aren't going to be that powerful, at least if I'm thinking about making accurate predictions about what we expect to see next. So in aggregate, I mean, there may still be value in that model that only explains 1% of the variation, but it means we need to take a prediction coming out of that model with quite a big grain of salt. All right, so that's a little primer on R², and I'll talk to you guys soon.